Okay. So if you have to begin with the unit speed curve, and the curve is unit speed, then everything you got is a geometry, geometry quantities. Okay. So here's a surface, and this is a curve, and this is gamma, and the arc length usually denoted by s. So so this is always assumption. Then you know, on the surface you have a plane, and this is a tangent vector. Sometimes denoted by t, sometimes just r, right? In geometry, when we put a dot on the top, it means this is derivative with respect to the arc length. When we put the r prime, it means this is derivative with respect to the arbitrary parameter. That's just a usual notation. So the second derivative, okay, and it's perpendicular to the first derivative because the unit length. This implies the second derivative perpendicular to the first derivative. Okay, so that means the vector you're going to get, here's another one, n cross gamma. It's going to be linear combination of these two. Okay, and that will be kgs, and this is the ns cross gamma dot s, right? So this is, we don't have a new name for that, just use this notation. So this is a curvature, right? Geodesic gamma is a geodesic, or the curve is called geodesic. There's another problem here. So so given curve on the surface, okay, there is essentially only one parametrization to that, okay, which uses arc length. Okay, if this start from point here is s equals 0, then I think this gamma is unique. Okay, so C is called a geodesic if the geodesic curvature is always 0 along this curve. Okay, that's a definition. Okay, now since then gamma s is a parametrization for the C, for the curve C, and then so sometimes we also say gamma s is geodesic. Okay, if the image is geodesic, actually we're talking about the image, the curve should be independent parametrization. Okay. So sometimes we also say gamma s is geodesic. Okay. Sometimes we say a unit speed curve is geodesic if the geodesic curvature is 0, or sometimes we also say that. Okay, so this is called the geodesic. It's also called a geodesic. Okay, we don't want to make them a difference. Okay, now so when we talk about geodesic, we're talking about the curve. Okay, it should be independent parameterizations, but this curve right now, this curve right now can be parameterized by arc length. Now maybe parameterized by another arc length, but the difference is only gamma and another gamma. You know, that could be slightly different by shifting only. Okay. So anyway, this is the definition, and then okay, then we find out this can be this is equivalent to saying that, right? Because equivalent to saying that this gamma s is a parallel to the normal vector field. Okay, this is another definition. Okay. Yeah, it's parallel to the normal vector. Okay. Yeah. So that means this is equivalent to say gamma s is a perpendicular to the tangent plane, right? So that's essentially different, but here s must be parametrization. arc length, okay, where S is arc length. Okay, arc length means i.e. the tangent vector of the unit has a unit length, unit vector. Okay. Right, so now I'm trying to find equations for the geodesics. That's today's main purpose. Okay, so since so you take an arbitrary surface patch, right? So the curves inside here, and over here you have U and the V, right? So this is the curve US VS, okay? And here's gamma, right? Gamma S is going to be sigma US VS, okay? We're trying to find equations for those curves, okay? Yeah, we're trying to find the equations on this function US VS, and that's the main purpose. Okay, so how to do that? All right. So, okay, now let's step by step this compute. Okay, so gamma dot, right, is going to be sigma u dot, okay, plus, for the simplicity, I'm not going to keep writing S here, okay? So that means that the derivative with respect to the arc length, gamma V and V dot, okay? The second derivative is going to be, it's two parts, right? The first part, sigma U dot double derivative, sigma V double derivative. Then I'm going to get sigma u, right, u dot, sigma uv, v dot, right, and u dot. And here, sigma vu, u dot, sigma vv, v dot, and v dot, right? So, so I can write this a different way. And this is going to be, sigma u dot square, twice of sigma uv, u dot, v dot, because that's 2, okay? Sigma vv, v dot square. That's pretty good. All right. Now, on the other hand, I have to recall the formulas. I remember earlier, this is a page. Yeah, we introduce a notation. Yeah, I'm going to find out the page number for you. Oh yeah, it's here. That is a so-called Gaussian equation. Okay, recall. Call the Gaussian equation. Okay, we call the position 7.4.4. That's called Gauss equation. Okay. And in the Gauss, we have sigma uu, and we introduce a notation like that. And then this must be L. This is normal vector, right? Sigma uv L m n and sigma vv, gamma 221 sigma u, gamma 22 sigma v, and n here. All right. Yeah. So where gamma ijk, okay, are expressed in terms of E, F, G, and their partial derivative. Okay, I'm not going to list all these formulas here. This is in the theorem. Okay, so partial derivative. It doesn't involve error. Okay, so put. So now what do you get, right? You will if you put it there, you put it into the above formula, right? I think I'm going to get, yeah, put all this here, okay? So so then you know, this gamma, right, can be written in some sigma u, something sigma v, and plus I think the second fundamental form here, because this is the LL, right? So put it there. This is going to be second fundamental form. Okay, so that is going to be yeah, the second fundamental form, and this is a part sigma. This is gamma, the second fundamental form. Okay, and in the direction of normal vector. Okay, so this part is yeah. Let's see what is this part, right? So eventually you can get this. Okay, I'm going to put. Okay, oops, the file is gone. Just bring it back. All right, so I'm going to keep a track on that. So let's see. Okay, I'm pretty sure this is u dot plus gamma 1 1 u dot square plus twice gamma 1 2 u dot v dot plus gamma 2 2 1 v dot square. Okay, that's sigma u. Just straightforward, right? All right. Then this is a linear part. Actually, it's on the tangent plane. Okay. Then I have this one. You know, this is L u dot square 2m u dot v dot and n v dot square. Right. That's the second fundamental form. Okay. So after plugging. So now it's clear that the first part. This is actually gives you the geodesics. Okay, this is actually the normal curvature. Okay, so this is going to be kg, right, and n cos gamma, right, and kn n, right. So this is a k normal curvature. Okay, so this is so k, this part is going to be this part, right? It's on the tangent plane, right? Yeah. Yeah. Look at this surface. This is the n. This is gamma dot, and this is a n plus gamma dot. So this is still on the tangent plane. Okay, this vector. Okay, it's linear combination. So we conclude that we get the following proposition. Okay, kg equals 0 if and only if this tangent part is 0, right? If only if you get u dot gamma 1 1 u dot square 2 gamma 1 2 u dot v dot, right? All right, so what that tells you, you get a system of second order equations, because they're not a linear equation. Six order ordinary differential equations. Okay. Right. So those are the equations because this is a curve, right? Curve is described by the surface patch here, you know, and here is a curve, right? So as long as you can describe the curve, because once sigma is fixed, as long as you can describe the curve US VS, right? Then you can describe the curve on the surface, and that is geodesic, right? And the U and the V satisfy this second order differential equations too, right? So you want to find the initial, this system of linear differential equations has a unique solution for any given, let's say S naught equals U naught, right? V naught. Okay, that's the first point. And then we also should have the initial condition. It's A. Okay, I'm going to use dot here. And it's B. Okay. So by ODE theory, okay, by the ODE theory, okay. So what does it mean here? For any direction of A and B at that particular point, and there's a unique solution here, okay. So gamma, you see, gamma ij, gamma ijk. Okay, look at this. Okay, gamma ijk. What is gamma ijk? Gamma ijk, I did not mention here. Actually, this is just U S VS. This is a function for you. It's a function, local functions on UV. Okay. So that's why they're not constant. That depends on U and V. Okay. So by the ODE theory, okay, for any initial condition star, there is a unique solution US VS, okay, satisfying the initial condition. Okay. Right. So that means on the surface, okay, if we take a point, take an arbitrary vector, okay, and then this vector can be expressed in the form A sigma U plus B sigma V, right? So this implies for any tangent vector in the tangent plane, there is a unique, any unit speed curve. Okay, this is a unit speed. Okay, that's going to be what? Okay, any unit vector. Okay, there's a unique geodesic C, right? Such that V is a tangent vector. Okay. Like given V, there's a unique curve going out, right? And in other words, a unique geodesic, or you can use gamma. Okay, gamma is that. It's going to be at the point P, and gamma, the tangent vector, is going to be the given vector. Okay, so that is a unique. Okay. Now, if a sigma is given, all you have to do is just focus on these equations. If you can find if you find the curve in the UV plane, then you get to the image on the surface. under the surface patch is going to be the geodesic on the surface. Okay. Yeah. So any curve here, right? The image will be this one. Gamma is going to be the image of this curve. Maybe this curve you can call gamma bar. This is a plane curve, right? Once you determine the gamma bar, and then you can get a gamma on the surface. Gamma bar is in the UV plane, right? So this is a very the geodesics can be completely determined by this. Okay. Now there are some other formulas also it's interesting. We can let's see. Okay. All right, so let's see, let's go back. Sigma u dot, sigma v dot, okay? And right, this is a geodesic. Right, tangent, a perpendicular tangent plane if and only if. Right. Right. This is going to be 0. Right. Okay, so what else? Well, how do we do the next? Yeah, let's all right, so now let's take a look at the first equation. Gamma, sigma u, right? This can be written as gamma dot, sigma u, right? Put it minus gamma dot, and they differentiate, right? So we can I can express here as u dot, right? V d dot, right? Okay. And the minus gamma, and this will be u dot, right? And sigma u v dot. Right? So when you multiply this out, yeah, let me put a ds here, right? I don't want to put a dot over there. So E dot, that's a E dot F V dot, okay, minus sigma u dot, I'm teaching. Okay, so you multiply this out. Okay, this is supposed to be 0, right? So I'm going to write this is supposed to be 0. Okay, so edu plus fv dot, and I'm going to multiply this out. So u dot, right? Sigma u, okay, and minus uv, right? And sigma v dot sigma uu plus sigma u dot sigma uv u dot v dot, and minus sigma v dot sigma uv. Yeah, keep a track of that. So so what do we get here? And this is supposed to be 0, right? Now I needed to look at what is this. This is going to be half of u dot u and u. Okay, so that means half of e. Right. And then sigma v dot sigma uu plus sigma u dot sigma uv. And that is going to be half of sigma v dot sigma u. I think it's u. Okay. Not only just half, I think I'm going to just equal to that. So that's just fu. The last one, sigma v dot sigma uv, is going to be half of sigma v dot sigma v and u. So that's a g u. So basically EFG, right? Again. So gamma dot sigma is equals, if and only f, ds edu dot fv dot is going to be, I think, is going to be half of this. That's eu u dot square, and f twice of fu u dot v dot, and the gu v dot square. Okay. Now similarly, similarly I can show that this is equivalent to this another equation, fu dot gv dot. Okay. This is the ev u dot square twice of fv u dot v dot and gv v dot square. So you get these two equations. Right? Sometimes those two equations are useful, but it's easy to see. Yeah. You can use the mattress notation. This is EFG, right? U dot V dot, okay? That is going to be half of that. Okay, half of what? This is a matrix. Actually, this part. No, can I use this matrix? Yeah, I tried to. No, I cannot make it easy. Okay, that's it. But this part, now we can probably write this each equation as simply you can write like this, and here's u dot v dot, right? The matrix. E, F, F, G, and then U dot. Okay, you can write it in this form. E, F, F, G, and V. Okay. I think the first equation is more useful, but secondly, the first theorem is more interesting than this one. This one just, you can use that to solve equations, okay? And the first one, you see, go back to here. This is yeah. You have to compute those coefficients first in order to solve this equation. Okay, but gamma ijk, they depend on EFG and the partial derivative. Okay, if you use a computer, it clearly this proposition is better because it's written in the standard form. The second order derivative of u and the v depends on u and the v and their first order derivative. This is called for nonlinear differential equations. So for any given initial data, you can find a unique solution out of that. Okay. For computers, yeah, this is a better result. But in reality, sometimes we are not able to solve by hand the above equations. So how can I determine some kind? Right? How can I quickly determine solutions? And those two equations those two identities are useful. Okay. Yeah, let's take a look at some examples. And really, the examples, maybe the second proposition is better. Okay, let me write down the proposition name. Okay. A unit speed, sorry, not a unit, a unit speed curve is geodesic if and only if a unit speed curve is a geodesic if it's satisfied by the following two equations. Yeah, actually, you can backforward. You can show that as equivalent to equation, if and only if. Okay. So now let's take a look at examples, and you see that you only needed to compute the first fundamental form, right? EFG, right? Either the first theorem or the second proposition. The first proposition, in either case, it does not involve L and N. Okay, so let's take a look at some examples. Consider curves on the sphere. So here's a sphere, right? Here's a standard parametrization. The sigma theta phi is going to be cosine theta, cosine phi, cosine theta, sine phi, sine theta. And that is the phi, right? And this is the angle theta. Right? So you can have theta is first. So theta is from 0 to pi. Angle here is from 0 to 2 pi. So you have a square, which is centered to a rectangle, which is mapped to the sphere. Okay. Some areas overlap, some areas missing. I think it's overlap, okay? Or collapse to one point, like this here. All right, so that's a sphere, and we know that the first fundamental form right? The first fundamental form determined by coefficient, so E equals 1, F is 0, G is cosine square theta. Okay. Yeah, this is already known. I don't need to repeat it. So I'm going to talk about this. Yeah, I'm translate. You see, the second proposition looks okay. Actually, is better in this in this. Yeah, in order to study the geodesics. Okay, so E, right? U dot plus F is already 0, right? Plus 0. So let's see. I'm going to translate. U is going to be, U is my theta, V is my phi. So U is a theta, right? F is going to be 0, so it's gone, right? Half of theta dot phi dot, right? And 1, 0, 0 cosine square 0, and that's a theta. And the second one, right? And the 1, 0, 0 cosine square theta, and that's a phi. Okay, let's simplify. Not phi here. F, this is a G. Okay, this is a G. Okay. G is cosine square theta. Yeah, let me put the details here. So that is F is still 0. So F right, and G yeah, okay. So let's simplify this equation. It's constant speed. We have addition that can constant unit of speed means theta dot square plus phi dot square cosine square theta is going to be 1. And that is our assumption. Right, let's simplify the above equation a little bit. I think that would be t cosine theta sine theta negative, right? And then c dot square. That's even zero, everything's zero, because this is independent field. So the second equation looks much better, promise, right, than the first one. This is a negative cosine theta sine theta c dot square. So that means by the second equation, this is going to be the constant, an independent variance. All right, so can we simplify further a little bit, right? So from here, phi equals c cosine square theta. I'm going to put it here. So theta square equals 1 minus phi dot square cosine square theta. So you can simplify the equations to this form. Theta square equals 1 minus c square divided by cosine. Okay. And I think we can solve for theta even, right? So it only depends on, yeah, it only depends on c, right? Cosine c. It's a function of c. And the first one, now we haven't used this equation yet, right? So you get once you solve for theta, once you solve for theta, then you can determine determine phi, right? Because theta, yeah, from here, see, this is body. So this is step here. Then from here you can, once you get theta, right? So you get a function of theta, theta. From here, you can solve for theta, right? Then once you solve for theta, then you get a derivative of phi from the above equation, right? Then you solve for phi. So, but it's a formula is pretty complicated in general, right? Now, what we look at a special case because sphere is around the sphere, right? So I want to show you why the grand circle is going to be the geodesic. The grand circle is going to be geodesic. Okay. We look at the case when look at the case when theta, yeah, when theta is going to be pi over 2. Okay, that's a special. Okay, so we assume that theta is constant, theta, and then you will get a grand circle, yeah, right? So let's see. If the theta is just function of s, it's constant, it's always pi over 2. Okay. Then the above equation Okay, let's go back to the equation. Okay. So the first equation, the data is going to be 0, right? Always. So that is going to be negative cosine and the sine theta and phi dot, right? And then this is a ds cosine square theta phi dot equals 0. And I think both are automatically satisfying because when theta is pi over 2, right? Okay. So this part, the left hand side is 0. And cosine pi over 2 is always 0, right? So those two equations is a right. Yeah, those two equations are satisfied automatically. Okay. So therefore, it's a geodesic. Okay. So square circles are geodesic. That's very important. And then, the sphere is around the sphere, you can put it in any position, right? So that's why great circles are geodesic. So my conclusion is great circles are geodesic according to our definition. Okay, there are several ways to prove the great circles are geodesic. This is one of them. Okay, we also use the previous theorem. Okay, the great circle will be the intersection of a special plane, okay, perpendicular to the sphere, and right, and with the sphere. So great circle, you get a great circle, then the great circle must be geodesic. But this is another way to prove the great circles are geodesic. Okay. Yeah, now let's take a look at the next problem. The circular cylinder. Okay, the circular cylinder. Okay, the circular cylinder. The circular cylinder actually is symmetric to the plane locally. Okay, so for this surface, you can show that they have the same. Yeah, let's take a look at the special surface patch. Okay, sigma UV is going to be cosine U, sine U, and the V. I think that's it. Okay, and so sigma U equals negative sine U, cosine U, and 0. Sigma V is going to be 0, 0, and 1. Okay, so now you have E equals 1, F equals 0, G equals 1, just like in the plane. Okay, and actually these two are assumed. Okay. Yeah. This is a U. That's a V. And this is a point. You can also define the surface factor for this special plane. So this is to an assumption, local assumption. Okay. That's a local assumption. So you have, okay, anyway, let's look at this, let's look at the cylinder. Okay, what I want to show is the curve on the cylinder is a geodesic if only if on this corresponding plane, they're strict lines. And that's what I want. Okay. So let's take a look at this. Okay. So E, F, G, they're all constants, right? Okay. So these two equations, then we have, I'm not going to compute the gamma ijk here. What I'm going to have here is yes, E is 1 U dot, right? Equals 0 because they're all of them 0. Okay, E, F, G are partial derivatives are 0. So this is the V dot, it's going to be 0. Yeah, just because E equals FU equals GU, they all equal 0. Okay, EV equals FV equals GV, they all equal 0. All right, and right, so that's why you plug them into, into the in the terms on the right hand side, they're all equal to 0. So that implies U dot is going to be constant. Okay, V dot is going to be constant. Okay, so I can find the general form. It's going to be AS plus K V equals BS plus I'm going to use K and H, for example, right? So that means the geodesics are in this form. But remember, yeah, this surface patch actually is a local assumption, local assumption. Okay, so this surface patch, right, this U and this V, right? I use from 0 to 2 pi, and V there's no restriction. So U equals AS plus K, V equals BS plus V, those are the geodesic. Those are the strict line. Okay. Those are strict line. U, V equals AS plus K, BS plus H. So there's an image it's coming over here. Okay. Those are the geodesics. Okay, these are geodesics. So geodesics on the cylinder are described as the images of a strict line from the using plane. Okay. So now you can see that, okay, geodesics on the cylinder are completely determined, right? And using those equations. Yeah, we solve that, and you can, in some special case, you can complete it. And this sigma, if you view a UV plane as a two-dimensional plane in three-dimensional space, then actually this is a sigma can be also viewed as an assumption, local assumption for between the plane and the surface. Okay. Anyway, so gamma s, which is the image type of this curve, and the sigma is a geodesic. And we did not compute. See, we just use the second proposition. I only mentioned two propositions here. Okay, the second proposition is very useful in computing geodesics. Okay, and otherwise you have to use a gamma 1, gamma 1, 2. You know those how many coefficients are lots, and then you have to go through and compute it. All right, let's go to the surface of a revolution. Those are sphere, the cylinder. Then let's consider a little more general. Okay, the surface of revolution. Okay, surface of revolution. All right, so I choose a gamma, and that's a special curve. Okay, gamma is going to be f of s 0 g of s, f of u g of u. Okay, so gamma prime u squared plus g prime u squared equals 0. Okay, then the surface of revolution is going to be fu cosine v, fu sine v, and g of u. Okay. One can easily get E equals 1, F equals 0, G equals F squared. Okay. Now, so now these equations, I'm going to, the geodesic equations. Okay, let's take a look. So this is in the UV plane. Yeah. Right. So this is geodesic equations on U and S, V and S. Okay. Right. So first of all, we got E. Right. E is 1. F is 0. Right. E is 0. F is 0, and GU. That's 2F FU. Mm-hmm. And DDS, F is 0, G is F of U, V dot. Right? And then half of EV and F and the GV. GV, I think it's also 0. Right. So the second equation looks pretty simple. So we get V dot And so those two equations describe the geodesics on the surface of the revolution. So I believe that this curve is going to be geodesic. I claim this is going to be geodesic. So when v is going to be 0, okay, so my uv dot here is going to be s. Yeah, let's see. When v equals 0, right? So you get a curve from top to bottom. So the first equation, and you will see that v dot is 0. So this is a v dot is 0, right? So this implies right. And the second equation is 0 and 0. That's always automatic second because v dot is 0. So that implies u should be equal to right. Okay, so that means yeah, let me go back to v. That's what is v. V is located, right? So that means when v is a constant, that means it's always a geodesic. Yeah, I can put a 0 here to be always geodesic. So gamma s not gamma. It's going to be f something, right? Cosine v and f something sine v and the g of something, right? So something here is just as plus b. So this is a geodesic. If sine v is 0, then just the curve. Right? So those are the geodesics from our computation. Okay. Now we also look at the case when we also look at, yeah, this is a second case. Is I just want to look at the circle, right? So u equals, okay? Then the above two equations, okay, let me go get the above two equations. No, they actually just look at the equation, right? So my v u is going to be constant. Okay, that is a circle. So we'll get these two equations becomes, let's do the problem slowly. Okay, so it's going to be 0 equals, let's look at this equation. The f prime of v, right? Okay, that's the first equation. The second equation is the derivative is f u and v, right? So that means the v dot, the second derivative, it's going to be 0. So that means the first derivative cannot be 0, right? So this implies, yeah, f prime u 0 equals 0. That vs is going to be as plus b. So if f prime u 0 is 0, then you get a Geodesic. Okay. So then us vs is 0 and as plus b is going to be a Geodesic. Okay, it's going to be the Geodesic. Right, how does a Geodesic look like? This is a picture. Right. So here, the shortest circle is a Geodesic because if you look at the value, f prime is going to be 0 at this point. Yeah, and yeah, that's it. So this is a function, right? Yeah, for example, for the smallest value, right? If f prime has a minimum value at this particular point, fu, okay, fu has a minimum value, then the derivative must be 0. Okay, so derivative 0, then the corresponding curve must be Geodesic. So we find that two type of geodesics on the surface of revolution, and I discussed that the last time. Okay, so you can see that in general it's difficult to describe the solutions. So this is the two general equations for the curves on the surface of revolution. Okay, those are the geodesics. These are two dots. Okay. But we just look at horizontal curve and then those curves. So those are the geodesics. Okay. That's it. There's some exercise you have to do, and most of the time you just needed to